From the very dawn of our sentience, we humans have gazed at the night sky, mesmerized by the silent ballet of stars and planets. Among them, one world has always held a special, almost magnetic allure: Mars. Our closest planetary neighbor, a rusty beacon in the cosmic dark, Mars has served as a canvas for our deepest longings and fears, a mirror reflecting our own existential questions. Is life a cosmic accident, unique to Earth? Or is it a common thread woven throughout the tapestry of the universe? And if so, might Mars, this seemingly barren orb, hold a piece of that story? A faint echo of a vibrant past? For generations, the dream of a living Mars has fueled our imaginations, from ancient myths to science fiction epics. But it is only now, through the relentless pursuit of knowledge and the ingenuity of our scientific tools, that we are truly beginning to peel back the layers of Martian history, revealing a picture far more complex and tantalizing than we ever dared to imagine. No. Our journey with Mars has been a long and winding one. For centuries, telescopic observations revealed only a blurry, reddish disk. Then, in the late 19th and early 20th centuries, astronomers like Percival Lowell famously misinterpreted surface features as a vast network of canals, fueling popular belief in intelligent Martian civilizations. This romantic vision persisted until the dawn of the space age. The Mariner missions of the 1960s and 70s, the first robotic envoys to the Red Planet, returned images of a heavily cratered, desolate, seemingly waterless world. The dream of flowing rivers and verdant plains evaporated, replaced by the stark reality of a cold, dry desert. It was a sobering moment for astrobiology, seemingly closing the chapter on Martian life. But science, unlike fiction, is rarely static. Our tools improved, our understanding deepened, and our gaze became sharper. Later missions, from Viking to Pathfinder, Spirit, Opportunity, Curiosity, and now Perseverance, began to paint a different picture, one filled with compelling, undeniable evidence of ancient water. We saw mineralogical signatures of past hydrothermal activity, sedimentary rock formations clearly laid down by liquid, and even the ghosts of ancient shorelines. The question was no longer times Mars had water, but how much, and in what forms. Were these merely isolated puddles, fleeting streams in a sporadic wet period, or something grander, something more akin to the hydrological systems we know on Earth? This is where the latest, truly groundbreaking research steps in, shifting our paradigm once again. What we have now uncovered is nothing short of revolutionary. Through the meticulous work of researchers, particularly those from the University of Texas, we now have compelling evidence that ancient Mars was home not just to isolated rivers, but to vast, interconnected hydrological systems, global in their reach. Imagine, if you will, networks of rivers, lakes, and deltas, so extensive they would dwarf many of Earth's modern river basins. The data reveals that Mars hosted no fewer than 16 major drainage systems, colossal arteries that sculpted the planet's surface. These systems collectively moved an astounding 28,000 square kilometers of sediment, accounting for a staggering 42% of all fluvial material ever identified on the Red Planet. This wasn't just a brief wet spell. This was an era of sustained, widespread liquid water, fundamentally reshaping our understanding of ancient Mars. The question that naturally arises is, how could we possibly reconstruct rivers that flowed billions of years ago on a world now seemingly devoid of surface water? The answer, my friends, lies in the elegant dance of technology and scientific ingenuity. The researchers employed a powerful combination of orbital instruments and sophisticated software. Primarily, they leveraged data from two key instruments on board Mars orbiters: the Mars Orbiter Laser Altimeter, or MOLA, and the Context Camera, or CTX. MOLA, as its name suggests, is a laser altimeter. It works by sending pulses of laser light down to the Martian surface and precisely measuring the time it takes for those pulses to return. By doing this repeatedly as the orbiter circles the planet, MOLA can create incredibly detailed and accurate topographical maps, revealing even the most subtle variations in elevation. These subtle changes, over billions of years, can still betray the faint outlines of ancient riverbeds, valleys carved by flowing water, and the depositional patterns of sediments. Complementing MOLA's altimetry data is the CTX, a powerful camera designed to capture high-resolution imagery of the Martian surface. While MOLA provides the vertical dimension, CTX provides the horizontal context, allowing scientists to visually identify features such as ancient deltas, meanders, and the broad outlines of valleys that once channeled water. It's like having both a precise contour map and a detailed aerial photograph. But the true magic, the scientific alchemy that transformed this raw data into a coherent understanding of ancient Martian rivers, came through the application of Geographic Information Systems, or GIS, specifically a powerful software called ArcGIS. I speak from personal experience when I say that GIS is an indispensable tool in geology and geophysics. It allows scientists to integrate and analyze vast amounts of spatially referenced data. Imagine layering MOLA's elevation data with CTX's visual imagery within ArcGIS. This software then enables complex spatial analysis, hydrological modeling, and the reconstruction of ancient landscapes. It's not just about looking at pictures, it's about using algorithms to trace the paths water would have taken, to identify where sediment would have accumulated, and to pinpoint the precise locations of ancient lakes, river deltas, and drainage basins, all based on the subtle erosional patterns still preserved on the planet's surface. This integration allowed them to literally retrace the flow of rivers that ceased to exist eons ago, uncovering the long-lost pathways of Martian water. This discovery naturally leads us to the most poignant question of all. If Mars once boasted such magnificent river systems, what happened to all that water? The answer is a stark reminder of planetary evolution and the fragility of conditions conducive to life. Mars was once a warmer, wetter world, but it lost its magnetic field. Earth's molten, convecting outer core acts as a giant dynamo, generating a powerful magnetic field that envelops our planet, creating a protective shield, the magnetosphere. This magnetosphere deflects the constant barrage of charged particles from the sun, known as the solar wind. Mars, being much smaller than Earth, cooled much faster. Its molten core likely solidified, or at least ceased its vigorous convection, effectively shutting down its planetary dynamo. Without a magnetic field, Mars was left vulnerable. The solar wind, unimpeded, began to relentlessly strip away its atmosphere, molecule by molecule. Over millions of years, the once thicker Martian atmosphere was slowly but surely eroded into the thin wisp it is today. And with the loss of its atmosphere, the planet's surface pressure plummeted. Here's where the peculiar physics of water comes into play. On Earth, at our atmospheric pressure and temperature ranges, water can exist as a solid, ice, liquid, or gas, vapor. But at Mars, current incredibly low atmospheric pressure and freezing temperatures, liquid water is fundamentally unstable on the surface. If you were to place a drop of liquid water on Mars today, it would simultaneously boil and freeze, rapidly sublimating directly from solid ice to water vapor. It skips the liquid phase almost entirely. The vast rivers and lakes of ancient Mars simply could not persist under these altered conditions. The water either escaped into space along with the atmosphere, or it froze solid, locked away in vast underground ice reservoirs, or within the polar caps, a frozen memory of a wetter past. The implications of this discovery are profound, rippling across several scientific disciplines. Foremost among them is the renewed quest for extraterrestrial life. We know that on Earth, river deltas and sedimentary basins are incredibly rich environments for life. They are natural traps for organic matter, nutrient cycling, and provide stable, aqueous environments. The identification of these 16 ancient drainage systems on Mars provides astrobiologists with highly precise and promising targets for future missions. Imagine a rover, equipped with advanced instruments, meticulously exploring the fossilized deltas of ancient Martian rivers, searching for biosignatures, the telltale chemical or structural evidence of past microbial life. This research doesn't just suggest where to look. It tells us exactly where to focus our efforts, dramatically increasing the chances of uncovering evidence of life beyond Earth. Beyond the search for ancient life, this knowledge is invaluable for planning future human missions. Understanding the geological and hydrological history of Mars is critical for identifying potential resources, such as subsurface ice, which could be vital for future human settlements. It informs us about the planet's past climate and geological processes, helping us to better understand the risks and opportunities for human exploration. The dream of one day making Mars a multi-planetary home, perhaps even terraforming it back to a wetter state, hinges on our deep understanding of its past and present. Ultimately, Mars stands as a stark, dramatic lesson in planetary evolution. It reminds us that having water is not enough. A planet must also maintain the conditions necessary for that water to persist in liquid form. It is a cautionary tale, yet also a beacon of hope. The ingenuity displayed by researchers, using tools like MOLA, CTX, and ArcGIS, exemplifies the relentless human spirit of inquiry. We continue to push the boundaries of our knowledge, reaching across the vast emptiness of space to piece together the narrative of our cosmic neighborhood. And with every new discovery, Mars becomes less of a distant red mystery and more of a familiar, complex world, one that continues to challenge and inspire us in our timeless quest to understand our place in the universe. That's it for today. If you enjoyed this deep dive, hit that subscribe button, stay curious, and keep your eyes on the skies. I'll see you in the next one.